Great. I'm delighted to introduce Marcus Brubaker. He's a close friend. We overlapped and worked together and shared an advisor at University of Toronto for 2 years. Some time ago, I'm not going to date neither myself nor Marcus by exactly saying when that was. Marcus is an assistant professor at York University and a faculty affiliate of the Vector Institute. From 2018 to 2020, for 2 years, he worked as a research director at Borealis AI. For those of you who may not know, Borealis AI is a machine learning research lab, sort of Canada-wide, funded by the Royal Bank of Canada, RBC. Marcus is also an associate editor for IET Computer Vision and has frequently served as an area chair for most top computer vision and machine learning conferences. He worked on a variety of topics, including Electron cryo-Microscopy, human motion estimation, autonomous driving, Monte Carlo methods, and many other things. And today he will talk about normalizing flows, which is a promising class of generative methods. So Marcus, take it away.
All right. Thanks, Leon. Thanks everyone for having me here and giving me the opportunity to speak. So I've actually worked on a lot of things over the years, and I kind of have a pretty diverse set of interests. And so I wanted to kind of just say a little bit more about my work generally and the kinds of problems that interest and motivate me. Oh yeah, before I really get going, feel free, if there are questions, feel free to interrupt and ask as we go along, or post in the chat if you want. I think Leon will be keeping an eye on the chat to see if there's questions that pop up there. I'm happy to be interrupted if there's things that are unclear. So carrying on, I just want to talk a little bit about the kinds of problems that are interesting to me, and the things that I've worked on over the years. And so my primary research area is in computer vision, I would argue, but I've done a lot of work and had a longstanding interest in machine learning and statistics, and more recently that's been a bit more of my focus. But even within machine learning and statistics, I'm really interested in ways that we can kind of take domain-specific knowledge and apply it to more general problems or otherwise intractable problems. The dogma of the last 10 years has been kind of a throw more data at it. That's starting to slowly shift in the last couple of years, I would suggest, but there's a lot of problems in the world that really can't be solved with just more data, maybe because the data itself doesn't exist or can't easily be collected. And especially if you go into industry, you'll find that, even in places where you expect to find lots of data, the data they have is not the data that you want. And so I'm really interested in how do we work in those spaces? How do we use the data that we have, as well as insights and knowledge about a problem that we might have? And in my view, computer vision is actually a really excellent example of that domain, because in vision, we are interested in understanding properties of the world based on the images that we perceive of the world. That's kind of the core problem, but we also understand a lot about how those images are formed. Going back to perspective projection, models of cameras and optics and photometrics, and the way that light interacts with surfaces. These are all things that have been characterized by physics and other disciplines for hundreds of years, literally. So we know an awful lot, and I'm really curious and really intrigued and try to work on problems and try to build models that can really exploit that information as well as possible, while also leveraging data and other things where available. So a couple of things that kind of fit into that line. I worked on STAN, which is a Bayesian statistical modeling package several years ago that's now being reasonably widely used. I worked on localization problems in robotics, where this was a paper from a couple of years ago, which was a lot of fun, where we were looking at trying to identify where in the world a vehicle was just based off of visual input. And so we were able to kind of leverage measurements of visual odometry, estimates of the direction of the sun, as well as map information, just having, the maps that you could download from OpenStreetMaps or elsewhere, and combining that together to get a system that was, able to localize a vehicle in the world to about 3 meters after, about 20 seconds of driving. Maybe 3 years ago now, I was working with a student of mine looking at texture synthesis. At the time, there'd been a lot of work on kind of style transfer, and we were trying to say, well, can we extend that to dynamic textures? And so indeed, we were able to extend some of these ideas of CNN-based models of texture to dynamic textures by kind of exploiting what we understood and what we knew about the properties of motion and kind of carrying some of those ideas over. This was a fun project with one of my students, Matthew Tesfeldat, who's now a PhD student at McGill, and Kostas Kapanis, who is a faculty member at Ryerson University. Another big area that I've worked on is electron cryo-microscopy. So you've probably not heard of this. Very few people have in computer vision and machine learning. It's not a commonly worked on problem, but it's a really interesting and important one in my view. This is the 1 minute, elevator pitch of cryo-EM. You have some purified sample of a biological molecule that you're interested in studying. So for instance, a virus, but also proteins and other things that are happening in biological systems. You spread it into a thin film and you plunge freeze it in liquid ethane. You stick it inside a transmission electron microscope and you get images out that look like this. And this is actually a real image. It's a bit of an old one now, but it's a real image. You probably can't see much on it. That's partly zoom, partly compression, but partly just the fact these are pretty terrible, low contrast, high noise images. If you look, there's some gray blobs in there that you might be able to perceive, and those all correspond to individual particles of that were in your sample when you imaged it. And the goal of cryo-EM is to kind of reconstruct these 3D structures. And so, this is on the surface of it, it's a problem that, a lot of people, you look at it, and I know certainly I did, and others that have worked with me have looked at it and said, is this even possible? But it turns out that we know an awful lot about how an electron microscope works and the physics of how that works. And if we marry that with just some basic ideas from computer vision and machine learning, we're actually able to reconstruct very detailed high resolution structures from this fairly atrocious looking data. And in fact, the very first structure of the SARS-CoV-2 spike protein was actually solved with cryo-EM, in fact, using some software that I developed in conjunction with a PhD student. And there's lots of other things. I've worked on some stuff in ballistic forensics, a little bit of medical imaging processing. We have a paper coming up looking at image recoloring with StyleGAN at CVPR this year. But the main thing that I'm going to focus on for this talk is normalizing flows. And this has been a research focus of mine now for maybe the last 2 or 3 years. And so what I'm going to do is I'm going to give a really quick intro to normalizing flows. And then I'll highlight go into a bit more detail on 2 projects of mine that have been done, with my students and interns over the last couple of years, and we'll go from there. But so please stop me along the way if there's any questions, and we'll go into that. So what are normalizing flows? So we'll start with kind of just a high level definition. So as Leon mentioned at the top, normalizing flows are a form of generative model, and they're built around the idea of invertible transformations. And they have a couple of properties which are generally pretty nice that are attractive as far as generative models are concerned. So one is that they're generally efficient to sample. So if X here is your data distribution, drawing samples, if X is the model distribution over your data, drawing samples from P of X is generally very relatively efficient. And it's similarly efficient to evaluate the density. And this is one of the kind of differentiating factors with normalizing flows in comparison to things like GANs and VAEs. So both GANs and VAEs is efficient to sample from them, but you can't easily evaluate the density function. Or in case of VAEs, you only have access to a analytic approximation, a stochastic approximation or a bound. Flows are also kind of highly expressive, and we'll talk about that maybe a little bit more later on. And as an added bonus, they're relatively straightforward to train. Now flows were originally introduced actually as a more expressive form of prior for VAEs in machine learning several years ago. And they didn't really get a lot of traction as a form of density modeling or as a form of generative model in and of themselves until this paper came out. So this was the GLOW paper from OpenAI in 2018. So these images here are randomly generated samples. So this was 2018. So these were at the time, arguably near state-of-the-art quality images for a generative model trained on Celeb A. Since then, of course, GANs have continued to improve. But this was the one this was the paper that certainly caught my attention, and I think the attention of a lot of people to say, hey, these normalizing flows have the potential to match the quality of GANs and VAEs, but without some of the downsides. They also have a fairly nice latent space representation that comes along with them. So this was another result from that paper where they were morphing between an image of one of the authors with faces of famous people, some of whom you might recognize. For instance, Jeff Hinton is in there. So just by interpolating in the latent space that was learned with the normalizing flow. So that's the high level pitch. Let's dive into the details here briefly. So I don't want to oversell them, because in my mind, at the end of the day, one of the nice things about normalizing flows is conceptually, they're actually pretty simple. Basically, they're an application of a basic result that you would have seen in any kind of introductory probability course, specifically the change of variables. Okay, so the change of variables from probability says, if you take some random variable x and you transform it by some function f into another random variable z, then the density of x and the density of z are related to this change of variables expression. Okay, and so you have, just to break this down a little bit, you have this invertible transformation f, and so one of the requirements for this equation to hold is that f here has to be invertible and differentiable. Okay, and then there's this additional term here, sometimes called a volume correction term, which is just the absolute value of the determinant of the Jacobian of that transformation f. Okay, and so you can kind of visualize what's happening here a little bit. If you think of, imagine you have some complicated distribution x, maybe it's this bimodal thing I have shown up here on the right. You run the random variable that this density corresponds to through a function. In this case, let's use f of x is just equal to the cube root of x. And just by running that random variable through there, you can apply the change of variables formula to work out what the density is. And it turns out that this corresponds to a nice, simple unimodal Gaussian distribution after that transformation. Okay. So this is change of variables. Again, this is kind of more or less what you would have seen in a introductory probability course. So what does that have to do with generative modeling for us? And so the idea is, let x here be your data, and we want to learn a distribution over x, or we want x to be kind of matching our empirical data distribution. And we're going to select a analytically convenient distribution over z. And now the learning problem is to find some invertible differentiable function f subject to this change of variables formula, right? So in other words, we're taking our images or our data distribution here, let's say some images of trees, and we have our fixed latent distribution over z. Let's say that's a nice, Gaussian distribution. And we're going to try to learn the mapping f that transforms this distribution of images into a distribution of zero mean, identity covariance Gaussian noise. Right? So how do we actually do that? Well, there are two pieces that we have to deal with or specify. So as I mentioned before, there's this kind of base distribution or base measure, again, typically selected zero mean Gaussian. And then we have the function f, which is referred to as a flow. And the constraint on f is that this has to be invertible and differentiable. All right. If we can do that and we can parameterize it, then we could learn the parameters of f, right? And try to map from this Gaussian distribution to the data distribution or vice versa. So if we have these pieces, and I'll talk a bit more about how we actually learn these in a minute. But if we have them, okay, then what do we actually do with this model? Well, density evaluation is actually very straightforward. If you have some sample x that you want to evaluate the density of under this normalizing flow model, change of variables formula gives that to you exactly. Okay. In other words, you start off with some image, you transform it through f of x, that gives you some point that kind of should look like this Gaussian noise. You evaluate the density under that Gaussian noise, And now you need to add in or multiply this additional volume correction term, which is the determinant Jacobian of the transformation. Okay. As I mentioned at the start of this section, we can also sample with this relatively efficiently, and basically that is going to exploit the invertibility of this function f. In other words, we sample basically by drawing a sample from this distribution over Z. So draw a sample of Gaussian noise, and then compute f inverse of Z on that, and that should transform you back into an image, right? Training of this is actually relatively easy, conceptually at least. There's no alternating minimization. There's no need to derive a bound. We're just going to train by trying to maximize the log likelihood of some set of data points, xi, and we end up with some sort of empirical risk minimization or maximum likelihood type estimation here, where we're trying to optimize theta, which are the parameters of this flow function f, this invertible differentiable transform. So that's the high level concept. Where this gets tricky, where this gets challenging, is these actual flows themselves. So it's a parametric function, these flows, which is invertible. That's one of the requirements from the change of variables formula. We have to be able to compute the inverse. That also means that f needs to preserve dimensionality. We can talk about that a little bit more later. Needs to be differentiable, strictly differentiable almost everywhere. It doesn't have to be differentiable everywhere, but that's mostly a minor detail. And has an efficiently computable inverse and Jacobian determinant. Okay, and this last point here is really just a practical consideration. If you have a function which is invertible, but its inverse is not easily computable, then you could still use it to construct a flow. But for instance, you might not be able to sample from it efficiently. Okay. By the way, just in the literature, these go under a bunch of different names: bijections, flow layers, etc. I might bounce around a bit between terminology myself. And so designing and understanding how these flows actually work is the kind of core research problem, the core research question around normalizing flows. And one of the reasons why this is hard, by the way, is that deep learning has shown us over the last 10 years how to construct really big, complex, nonlinear functions in kind of very nice composable ways. But this invertibility constraint is a bit of a tricky one to deal with. Okay, but like deep learning, we're going to kind of use composition or depth as a way to build up complex transformations from simple building blocks, and that's just exploiting the fact that if you compose invertible differentiable functions, it remains an invertible differentiable function, right? So in other words, if I have f1 up to fk, which are all individually invertible and differentiable, then we can compose them together and we get one much bigger, potentially more complex invertible differentiable function. Okay, bigger bijection. All right, we can kind of think about this gradually, and this will actually get us to at least a rough interpretation of where the term normalizing flows came from. If you think about having some very complex distribution here, and you apply your first invertible function, f1, and all f1 here maybe is going to do is kind of smooth out the two modes on the left, and then maybe reduce the mode on the right just a little bit. Okay, so this is a relatively small change to the distribution. And we could apply another invertible transformation, another bijection here, which will again kind of smooth out the modes on the left, try to damp down the third mode on the right there. And we do this again with 3. And each one of these transformations are relatively small variations on the distribution until finally your last transformation ends up converting this thing gradually into a Gaussian distribution. So this way you kind of constructed this, this complex change from a simple Gaussian distribution or between a simple Gaussian distribution and this kind of more complex wiggly distribution on the left. And then the inverse of this is just easily found by kind of composing the inverses of all these individual functions, which allow us to kind of map not from the complex distribution to the simple one, but from the simple distribution back to the complex distribution. So if we have some good simple building blocks of these invertible functions, we know we can build them up and make more complex things with these compositions, just like we do by adding more layers or adding more depth in kind of traditional deep learning models. But what are our building blocks going to be? So a simple one that we could think about is a linear transformation. Linear transformations can be a flow. The matrix, if the matrix is invertible, its inverse is nice and easy to write out. And the determinant is just the determinant of the matrix A. The determinant of the Jacobian is just the determinant of the matrix A. So all of that is fine. The problem is a relatively obvious one, which is that it's not terribly expressive. Okay, linear functions are closed under composition. And as a consequence, if you just stack a bunch of linear flows together, you're still stuck with a linear flow. But it'll turn out these linear flows are going to be useful for us in a number of other places. One of the other issues potentially is that the determinant inverse operation here could be cubic in the worst case, which could be quite expensive if it's very high dimensional. And so there's lots of tricks, diagonal approximations, orthogonal decompositions, and things like that that people use to get around this whenever they're using linear transformations. But again, the inexpressiveness of the transform is kind of the key limiting factor here. And so the way to get around that, or one way to get around that, which kind of is what sparked normalizing flows generally, is this idea of a coupling flow. Now, there's lots of other types of flows, and I'm not going to go into them. I actually have a whole tutorial about normalizing flows that if you're interested in learning more, you're welcome to. But I'm just going to cover coupling flows because they were kind of the seed, the initial idea, the initial thing that really started to bring these normalizing flow models to success. And so what is a coupling flow? So it's basically a general approach to constructing a certain class of nonlinear flows. And the way that it works is you're going to partition your parameters into two disjoint subsets. So you take your X, you split it into XA and XB, and then you're going to transform them and you're not going to transform XA at all, the parameters that fall into that first set. You're only going to transform the second set, XB, where F hat here is just going to be some other flow. Could be anything, could be simple, could even be a linear flow. But the interesting thing here is that theta is going to be the parameters of this simpler flow, is going to be a function of XA. Okay, so if you think about this conceptually, what you're able to do here is you're able to induce complex nonlinear correlations between the two halves of your parameter space, because theta here could potentially be any nonlinear function we want. So let me just illustrate this. So we take our X, we're going to split it into two pieces, XA and XB, and XA is going to be completely unchanged. All right, we're not going to touch that, but we are going to run it through a coupling network, theta, and that's going to produce a set of parameters which are going to control or define another flow, another invertible differential transformation, which will be applied on XB. Right, this is going to be the coupling transformation. It's applied on XB, and then we combine those two things back together, and we have our resulting output. Okay, so this is the entire transformation written out in different notation. Now, the inverse of this, because XA here is unchanged when we do this transformation, then the inverse of that part's relatively easy. So if we start in the other direction, imagine we have Z here, which is the output of that. We again split it up. We have ZA and ZB. Now ZA is just equal to XA, so that's just the original thing. So again, we're just going to keep that unchanged, and that's going to come over here. But because it's unchanged, we can also run it through our coupling network, and we'll get back exactly the same set of parameters that were used in the forward the forward computation, these coupling networks. And now we run these through the inverse of the coupling transformation, or sorry, we run ZB through the inverse of the coupling transformation. And we can now concatenate these things together, okay? And so now we have the inverse of our transformation. So we have this nice construction, which allows us to kind of get a little bit of nonlinearity in there. We can invert it, but there's kind of two things left to explain about coupling flows, at least two, I guess. One is that it's a little bit of a weird construction, feels a little bit artificial, and I haven't told you how we compute the determinant of the Jacobian yet. And these two both have basically the same answer. So if you write out the Jacobian of this transformation, you're going to get a block matrix that looks like this, or a block triangular matrix. So the top row is just going to be the identity and 0, and that just corresponds to the fact that XA remains unchanged. And then the bottom right entry of this Jacobian is going to be the Jacobian of that coupling transformation applied to XB. And then the bottom left is going to be the derivative of the coupling transformation with respect to XA. But note that we don't care about the actual entries of the Jacobian for normalizing flows. We only care about the determinant, all right? And so the determinant of this whole thing, the determinant of a block triangular matrix is just the product of the determinants of the blocks on the diagonal, okay? And so the determinant of the identity is, of course, 1. And then we were just left with the determinant of the Jacobian of the coupling transform itself. And so the whole point of this and the whole reason why coupling transforms are useful and practical is the fact that this theta really can be anything, and it doesn't impact our ability to invert the transformation, and it doesn't and what happens in theta there doesn't actually have any bearing on the determinant term either, right? The how computable it is just a function of what coupling flow you actually use. Okay, so what types of transforms do people typically use? They are actually shockingly simple. The first paper that really kind of looked at these ideas in these terms was nice and actually kind of an ICA type, nonlinear ICA type approach, where they just used an additive coupling transformation. So literally just add some constant t. But remember that t here in this constant in this context is a function of the other half of your parameter space. Probably the most widely used coupling transform is an affine coupling transform, where it's just kind of a diagonal linear matrix multiplication. So you have these element-wise scaling operations S and T. But again, recall that S and T are potentially nonlinear functions of the other half of your parameter space. And people have explored lots of variations on these coupling transforms, MLPs using CDFs or splines and lots of other things. Despite that, affine flows are still kind of the most common, and all they really boil down to is replacing the coupling transform here with an affine transform, okay, and replacing this piece here with that element-wise affine transformation, and that gets us the affine coupling flows, which is the foundation of things like real NVP, GLOW, and lots of other models, including the work that I'll be talking about next. So this is my reasonably quick introduction to normalizing flows. If you have any questions, ask now, but otherwise we will go on to an application of normalizing flows. So this was a paper from a couple years ago, 2 years ago now, I guess, ICCV, looking at modeling camera noise. And so in computer vision, if we start off with a camera, we take some picture, we look at this, and we don't get just an image out when we take a picture. We get an image that's been corrupted by noise. And so if you zoom into this little patch here, for instance, you'll see that even on this reasonably nicely exposed image, we can see some significant noise in our image, right? These regions clearly should be constant. And so we have this noise here. And let's just take a bit of a closer look at it. We can get a clean version of this image, and we can subtract it off, and we're left with just the effectively what the noise looks like. And at first glance, this might look Gaussian, but if you actually look at a histogram of the noise, we see that it's definitely not Gaussian. So this is kind of the best fitting Gaussian to this particular distribution. And in fact, that is masking an even more pernicious problem with this noise, which is if we scale up the noise, what we see is there's structure to it. It's correlated. And that's because the noise itself is signal dependent, right? So it's actually a function of the underlying intensity of the image, of the light that's impinging on the sensor. And so you can actually quantify this. So this is just looking at noise variance, empirical noise variance as a function of signal value, right? And what we see is this very nice linear trend that the variance increases as the intensity increases. And this is, of course, should not be particularly surprising to people that have studied physics, because we know that photon counts should follow a Poisson distribution, where the variance scales linearly with the mean of the distribution. And indeed, if we fit a line to this, we get a pretty good fit. But it's not a perfect fit. And in fact, there's lots of other things that are going on in cameras and camera images that are not Gaussian or not even this kind of signal dependent, Gaussian type model, right? So we have dark signal non-uniformity throughout the image where effectively black is not black. We have things like defective pixels where there are pixels that are always either bright or dead. There's clipping over and under exposure. There's noise that gets added in during gain. There's thermal noise and all sorts of electronic noise. And basically, the whole process by which the photons that strike our sensor, which are corrupted by this kind of nice and neatly characterized Poisson noise from physics, gets transformed into a raw RGB image that we read out of our camera, involves a whole lot of other steps that both apply nonlinear transformations to this distribution and potentially introduce new sources of noise. And so the idea behind this project was to try to learn a convenient and compact model of camera noise that exploited this knowledge using normalizing flows, okay? And that model is what we ended up calling noise flow. And so I'm just gonna walk you through the steps of it and you can see all the details in the paper. But so we start off with Gaussian noise. And remember, if you think of that, the diagram on the left, we start off with photon noise or Poisson noise. And so we know that that is reasonably well captured by this sort of linear dependence on intensity. And so we start off with a signal dependent normalizing flow transformation, where basically we scale up this Gaussian noise by some scale factor S, where S is going to be a function of the clean image intensity for the corresponding pixel and channel, okay? And so this is basically our signal dependent Gaussian noise, or what's sometimes called a heteroscedastic camera noise model, okay? But if you think back to the figure from the last slide again, next we have a whole bunch of stuff. There's electronic noise, there's thermal noise, there's readout noise, there's lots of other stuff that happens in here that we don't really know how to easily or conveniently represent. And so we're going to just plug in some affine coupling layers, okay? So we're going to just plug in these blocks of kind of, well, think of them as like a black box of stuff happens that we don't know. And then we know that we have a gain step in here, and that gain step is going to be a function of the ISO settings of the sensor, as well as potentially varying between cameras, because obviously different cameras, different sensors have different noise characteristics. And so we introduce a gain layer here, which is a function of both the ISO setting of the camera, as well as kind of a discrete identifier for each individual camera model. And then we have readout and quantization and lots of other things that kick in. And so we're going to have another set of these kind of black box affine coupling layers, these normalizing flow layers, until finally at the end, we're going to get out our camera noise. Okay. So this is the model that we're going to have. And we're just going to train this on clean and noisy images, on examples of camera noise. But that does, of course, raise the question, where do we get those samples from? Okay. And so we use this SIDD, the smartphone image denoising dataset. It's collected by the student that did this project, Abdulrahman Ahmed, had previously in his PhD work collected this smartphone dataset. If you've ever thought that it was easy to collect data for denoising applications, I would encourage you to go read this paper. It turns out, if you want realistic examples that are not corrupted by weird things like lighting variations and subpixel shift caused by hardware optical stabilization, it's actually incredibly difficult to do. But Abdul had done this and created this great data set that we used, which is really just perfect for our purposes for this project. And so what we did was we took this data set and we basically learned the flow model that I described previously, the noise flow model on it. And so here are some images that just qualitatively we can look at real quickly. So we see on the left here just simple Gaussian noise for a corresponding clean patch. And then you have the real noise, which is in the fourth column there. And we can see very quickly that the Gaussian noise is not a particularly good fit just qualitatively. The camera noise level function, which is effectively just a heteroscedastic Gaussian noise model, looks definitely better than just the pure Gaussian model, but not quite realistic. And then noise flow, which looks pretty good. But of course, unless you're an expert in camera noise and spend all day looking at these images, you're probably not going to be able to tell the difference. And so we did, of course, evaluate this quantitatively. And so, for instance, we could just look at the negative log likelihood on a held out data set, and we see that we get pretty significant improvements using noise flow. We also looked at the marginal statistics of the distribution of sampled noise, which is this marginal KL. We could look at the KL divergence from marginal statistics. And we found kind of good quantitative improvement by introducing this noise flow model. But one of the most interesting things I think we did with this was we used it to train a denoiser. And I'll go through this quickly just in the interest of time. But basically, we trained a DNCNN, which is kind of a standard denoising, deep learning denoising architecture. We trained it using synthetically generated data, which is the first 3 rows of this table. So the first row, we took clean images and we corrupted them with Gaussian noise with various standard deviations. And we trained that, and we got 43.6 PSNR for DNCNN. We took the camera noise level function, which is that heteroscedastic Gaussian noise model, and we trained that, and we got about 45 PSNR. And we trained noise flow, and we got basically a 3.5 decibel improvement by training with the right synthetic noise, or at least much more realistic synthetic noise compared to the camera noise level function. So that was really nice. But I think the interesting thing that we saw here was, we trained noise flow with clean noisy image pairs. Why don't we just train the denoiser with those same clean noisy image pairs? And that's what this last row, the real row here, shows. And it turns out that you actually get worse PSNR by training your denoiser directly on the real data itself than by synthetically generating data with noise flow and using that to train. Which was really surprising. I mean, we were happy to see it because it's a good result, but it was a little surprising and confusing at first. But I'd argue that it actually demonstrates that when we're training models to do tasks like denoising, but frankly anything that we're doing on images, if we want the model to be robust to noise, we're not just training it to recognize noise. Even in the case of a denoiser, we're also training it to understand what natural imagery looks like. And as a consequence, using these sort of simulated synthetic noise, so long as the noise is realistic, we're able to show our model when we're training it a much wider variety of realistic imagery. Okay, so that was noise flow. There's lots of other stuff kind of going on here that's kind of interesting. Lots of interesting future directions. I'm kind of keen on trying to use these ideas for noise modeling for other sensors and imaging domains. You can imagine trying to extend these models to capture other aspects of camera noise, things like fixed pattern noise or more detailed camera specific behavior, as well as trying to look at using these realistic models of camera noise in other applications. So of course you can check out the paper for full details.
Marcus?
Yeah.
To stop you, there is actually a question from an earlier part, which
sure.
Someone asked in the chat. So does it matter how much of X is being split into XA and XB? This was back when you were talking about
the coupling transformations.
Yeah.
It's a great question. It turns out not strictly. Like what matters most is that you alternate the splitting and you kind of mix up how things get split into those halves. Because if you notice, XA doesn't get manipulated at all. So if XA was Gaussian to start, it's going to be Gaussian to finish. And so typically you interleave these affine coupling layers, or these coupling layers generally, with either permutations, like random permutations, or you the 1-by-1 convolutions is effectively kind of a local or a diagonal form of linear transformation, which kind of mixes how things get split. So you have a fair amount of flexibility in it. You just need to make sure that you're actually kind of, all dimensions are getting kind of the opportunity to be transformed in a similar way.
Cool. I just have a quick question on the previous slide.
Yep.
So For this result where you were using noise flow, were you
Yeah.
doing this with the same number of images, or how did the number of images play into this?
The number of, so they were all, I mean, all of these methods were trained with exactly the same set of clean images, and they were all trained for the same number of epochs and iterations, and therefore they had the same number of epochs and iterations. But one of the differences, for instance, between the noise flow instance and the real data instance is that, you know, you have only a finite number of noise samples for each clean image in the real data. And so inevitably the training with the original raw data would kind of get repetition. Yeah.
Okay, so you sampled a different noise image or sort of for every epoch or something.
Yeah, so for noise flow, you basically, when we were training, actually for the first 3 lines, the way it would work is you'd sample your clean image from your training set, and then you would add randomly sampled noise on that, either from the Gaussian model, the camera noise level function, or from noise flow itself.
Got it. Thank you.
Yep. Okay. Any other questions before I move on to the last piece? No? Okay. Great. So the last piece is wavelet flow, and so this was, I should say, this is work done by my then master's student, now PhD student, Jason Yu, in collaboration with Kostas Strapanis. And what we wanted to look at, what we got kind of interested in, was scale structure and generative models. And so at that time, existing normalizing flow architectures lacked explicit notion of signal scale. And I say signal scale here because if you're familiar with normalizing flows, you might be familiar with the kind of multi-scale version of normalizing flows that have been introduced was originally introduced in Real MVP and is reasonably widely used. That is a slightly different notion of scale that I'm happy to talk about if anyone wants to. But the signal scale, the scale of the signal itself, is not really expressed in those models. And so one of the byproducts of this fact, for instance, is that models trained at different resolutions can be wildly inconsistent with each other. So you can train a model successfully at 256 square and then train another model at 128 square on exactly the same data. And you get, maybe the model at 256 square works and the model at 128 doesn't, for instance. There's this kind of general inconsistency between that's dependent on resolution potentially. It also means that training is expensive. Classical techniques in computer vision for dealing with high resolution imagery involve things like coarse defined approximations, and you really can't do that with this. The GLOW model, for instance, I alluded to earlier, it was high resolution in that it trained on 256 square images, and it took almost a year of GPU time to do that training. Right? It trained for about a week on 40 GPUs. For that result. Now, scale structure and generative models is not new generally. So GANs and BAEs, for instance, have been exploiting things like image pyramids and other representations of image and signal scale in their generative models. So for instance, this is a figure from LapGAN, which basically trained a GAN to generate the levels of a Laplacian pyramid, and then take the Laplacian pyramid transformation to reproduce the original image, or reproduce the generated image, I should say. But this hadn't really been done yet in normalizing flows. And so, we initially actually looked at image pyramids. They obviously have a long and kind of fairly successful history in computer vision, Gaussian pyramids and Laplacian pyramids and lots of others, but they have kind of one key problem when it comes to normalizing flows, which is that they're overcomplete. So if, for instance, you want to model the distribution of Laplacian pyramid coefficients, you're modeling, 30% more coefficients than you actually have pixels in your image. And that means that change of variables that gives us the ability to do exact density estimation all kind of goes away. And so in order to maintain invertibility, as well as the ability to do exact density computations, we need to preserve dimensionality in our scale space representation. There's lots of other scale space representations that you could look at. For instance, the Fourier transform would satisfy this. It maintains invertibility. It would allow exact density, but then that would mean constructing a generative model over the Fourier coefficients of a signal, which seemed a little bit harder because you lose the spatial structure of your image, which we rely on heavily with convolutional architectures. And so our solution to this problem, our proposal, as you could probably guess from the title, is wavelets. All right. So the space of wavelets is a very big space in signal processing that I'm not going to pretend to go into and give a review of, but I'm just going to give a flavor of how wavelets work. And so the wavelet transform is basically a scale-wise decomposition of an image. And so imagine you start off with this image here. When you run it through the wavelet transform, what ends up happening is you get a low-pass filtered half-resolution image. So that's this image here. So now you've cut the dimensions in both axes in half, and you have a set of detail coefficients. And these detail coefficients basically are everything else. It's all the other stuff that you need to reconstruct your original high-res image in conjunction with that low-res image. Okay, and so you can just make this a bit more concrete by putting some dimensions on this. So if you have an n square by 3 image here, then maybe your low-pass, your low-res, your low-pass filtered version is n over 2 square, and then your detail coefficients end up being n over 2 square, but with 3 channels per RGB channel, or n over 2 square by 9 channels. Okay, so if you do the math and you add this up, you'll find that the dimensionality of your signal is actually being preserved here. And with the wavelet transform, this scales your image down by half, but you can kind of continue to apply the same wavelet transform again on your lower resolution image, and you again get another, yet again, lower resolution image, another set of detail coefficients, until ultimately you can just keep your lowest resolution image, however far down you want to go, and the detail coefficients. And if you have those, then you can use the inverse wavelet transform to go back and reconstruct your high resolution images incrementally. So you take your lowest resolution image and your detail coefficients, those get passed through the inverse wavelet transform to produce the next next higher resolution image, which then gets again combined with the detail coefficients of the next level through the inverse wavelet transform to get back to your original one. Okay, so this is high level intuition of the wavelet transform and the inverse wavelet transform. So formally, we can just write this out like this, where basically h here is a function which kind of applies that wavelet transform progressively over and over and over again until we're left with kind of our lowest resolution image, I0, which could, for instance, just be a single pixel with three channels, and then all the detail coefficients that came along with it. Okay, and so this function h here that kind of applies this wavelet transform has a couple of nice properties. So it preserves dimensionality, which means that it's potentially invertible. It's not sufficient, but it is necessary in this case. It's also the case that the wavelet transform is linear, right? So that downsampling operation and the production of the detail coefficients, all of that is effectively just filtering. You're just doing convolution, okay? And that means that the transformation is differentiable, and because it's linear, that means it would have a constant determinant. So we've kind of checked off 2 of the boxes. And now, in fact, if you choose the right family of wavelets, this transformation becomes orthonormal, meaning that the determinant is 1, therefore it's fully invertible. And in fact, because the determinant is 1, it becomes very convenient to use it in the context of a normalizing flow. Okay. And so in practice, we use the orthonormal version of the Haar wavelet. You can use other wavelets, by the way. We've played with it a little bit. Turns out it's not terribly interesting, may not be a good idea for a variety of reasons, but we use the Haar wavelet primarily in the paper. And now, what are we going to do with this Haar wavelet decomposition? Well, let's start off by just using the change of variables, see what happens to the distribution over an image when we apply the change of variables from the wavelet transform, right? So we have P of I here on the left. Change of variables gives us this joint distribution over the lowest scale image, I0, and all of our detail coefficients. And now we can use the product rule of probability to factorize this, okay? And so now we can just write this as the product of P of I0, so our lowest resolution image, and then the detail coefficients conditioned on the lowest resolution image, and then the next level of detail coefficients conditioned on the previous detail coefficients, the previous image, and so forth, okay? Now, the last step that we can do here to get to kind of the last step in this derivation is to actually apply that inverse wavelet transform that I just described. Okay, and what that really means is that if I take the lowest resolution image I0 and all the detail coefficients up to level I can exactly compute the image at scale I+1. And so that means all of this factorization can just be written as I have here at the bottom as the probability of my lowest resolution image, and then the conditional distribution of my detail coefficients at a particular scale, given the image at that scale. Okay. And because of the orthonormality of the transformation, we don't have a determinant term that shows up in here anywhere because the determinant is just 1. All right. And so that is wavelet flow in a nutshell. Okay. And we train it using maximum likelihood. But one of the advantages of doing this is that if we take the log probability of a given image, it splits out into this form. So we have the log probability of our base image, and then a sum of the log probability of the detail coefficients at each level. And what that means is that the distribution of the base image and the conditional distributions of all the detail coefficients can be trained completely independently. They can be trained in parallel. They don't have any relationship to each other at all in this structure. Okay. Now I'm going to get to results in just a second here, but in practice we used kind of a glow-based normalizing flow architecture for both this base image distribution as well as the conditional distribution of all the detail coefficients. Okay. So before I get to the results, let me just show you quickly how generation works with wavelet flow, because it's not just a single forward pass of a model. The way we do it is we first draw a sample from our base image distribution. So that's going to produce this low-res image. Now that low-res image is going to be conditioned to get the distribution of the detail coefficients at that scale. And then those are combined together through the inverse wavelet transform to get the image of the next resolution up. And then this process is repeated again to generate the detail coefficients at the next level, which are then combined to produce through the inverse wavelet transform to generate the high resolution image. Okay. So we trained this on a bunch of different data sets. And I know it's always de rigueur to have a table with bold numbers, but the student who made the slide does not like tables, so he decided to make a graph, which is fine actually, because the point here is not that we're going I'm not going to try to convince you that this is going to get you a significantly better quantitative result. Some data sets we get slightly better results. So for instance, we do a bit better on ImageNet. Other data sets we do just a little bit worse. For instance, some of the LSUN data sets we do a little bit worse. But the point is, we get results that are comparable to GLOW and real MVP, which are kind of the natural baseline comparisons for the method. But I do want to draw your attention to the bottom two lines here, which are Celebe high quality and Flickr Faces high quality. And there's no competing bars from real MVP and GLOW here, because this is trained on these data sets at full resolution, so at 1024 squared. So previously, all the above data sets are, at best 64 by 64. And for the most part, no one else had trained anything at 1024 square with normalizing flow before. And they typically been working on much lower resolution or downsampled images. Whereas with Wavelet Flow, because each scale is trained independently, we can actually parallelize it very efficiently, and the models themselves don't need to be as individually complicated as they would be for one monolithic model of a high resolution image. Beyond being able to train on these really high resolution data sets, training is actually significantly faster. So this is just a comparison in GPU training time between GLOW and ours. This is based off of what we could determine for the GLOW training time because we didn't have 40 GPUs to spare to retrain Celebe high quality at 256. But basically, in the case of the Celebe high quality at 256, we were able to get about a 15x speed up in training time. Similarly with LSUN, we were able to get about 7x speed up in training time over GLOW. Now, one of the cool things about this model is that we basically get super resolution for free. So let me just show you an example. So if you think about the diagram I had previously, where I was showing you the sampling process, at any point there, instead of putting a sampled image and then conditioning on it and generating the detail coefficients. You could put in a real image and generate the detail coefficients for that image at that scale and construct a higher resolution image. And so this is a 128 square image from Flickr Faces, and we're going to do an 8x upsample on it. So I'm never really sure how much the compression from Zoom will hurt what you see on this. This is fairly pixelated. And then here is our 8x upsampling using samples from Wavelet Flow. And the one thing I'll note is that there's been a bunch of people that have looked at generative models recently for super resolution, which is, I think, it's a very natural fit, especially for kind of these more extreme degrees of super resolution. But in many of those models, there's actually nothing that, there's very little that ensures that the super res image is actually consistent with the lower resolution image. In fact, the generative model basically has to learn to do that itself. Whereas with Wavelet Flow, we're actually, we can guarantee that this 8x upsampled image, if you did an 8x blurring and downsampling, you would get back exactly that original 128 square image. This is the original image, by the way, for reference. So this is upsampled with Wavelet Flow. This is the original. It's a little hard to see, especially over Zoom, but if we can zoom in and show some crops. What we find is we lack a little bit of high frequency detail, but we're actually doing a reasonably good job of kind of upsampling and doing this. And I should note that super resolution was not a goal of what we planned to do here. This was just kind of an experiment that we added in because we realized that it was there for free as part of the model. So here's just a quick summary for Wavelet Flow. Each one of these kind of conditional detail coefficient distributions can be simpler and can be learned independently, which enables this parallelized and fairly highly efficient training for high resolution signals. I should also add that basically every model includes a consistent low resolution model. So if you think about that generation process, if you stop at any given point, you don't have to run to the highest resolution. You can stop at any point, and now you have a model of a 128 square image, even if what you originally trained for was 1024 square. It also includes kind of super resolution effectively for free. It's not a panacea, I will freely admit that. Perceptual quality is a bit limited. Quantitatively, our results suggest that it's on par with the baselines, but the perceptual quality is a bit limited. We have some theories about why that is, but we're not 100% certain just yet. And one of the things I would really love to do is try to run on other kinds of signal. So 3D data like MRI or CT, I think 3D signals in particular would be very, very natural for this. I think you could train on really high resolution 3D signals that just would not at all be tractable with any other, kind of generative model, or at least any other normalizing flow model. That'd be really cool to do. So if anybody has data like that and is interested in generative models on it, feel free to reach out. I've done a bunch of other stuff in flows recently that I'll just really quickly allude to. So one is we've been looking at kind of expressiveness and trying to understand how these distributions work. So there's there's the universal approximation theorems for normalizing flows, which is great in the infinite capacity, infinite data regimes. But I'm kind of curious what happens when we, in actual reality, when we work with finite data and finite capacity models. And one of the things that we found, for instance, was that the tails of our distribution don't actually get modified or don't actually get learned in normalizing flows, at least with kind of typical construction of normalizing flows. This was an ICML paper from last year where we showed this, and we were able to generate show some ways to fix it or work around it. This other one was a joint project with Roishi Deng, who's a intern at Borealis and a student of Greg Morey's at SFU, looking at applying normalizing flows to construct continuous stochastic processes that have nice properties, such as being to be able to do exact interpolation and extrapolation of the distribution of the stochastic process while being more expressive than something like just a simple Wiener process. And then this is actually work under review right now, where we use normalizing flows to learn density estimation on manifolds by generalizing this dequantization trick. So with that, I'm going to stop because I'm more or less at time. So thanks very much for your attention. I'm very happy to answer any questions, and I'll just give a bit of a plug. If you're really interested in normalizing flows, I'll be running a tutorial on these again at CVPR this year. All right. Thanks.
Thank you, Marcus.
So does anybody have any questions? You can use the raise hand feature. Oh, there's one, Helga.
Yeah, hi, thanks for the great talk. I really enjoyed it. I haven't really played around with it myself, so this is really for me to get some insight on how these things work. I wondered what doesn't work for the normalizing phase, or where are still the difficulties. I really have not a good intuition how these, how these invertible operations, what they can do and what they can't do. So do you have any practical experiences where it didn't work or where you faced difficulties?
Sure. Yeah, so I mean, you've actually kind of hit the nail on the head in terms of where the practical difficulties lie with normalizing flows, which is what are these, the intuition. I mean, we like to think about deep learning as constructing these big black box transformations for classification or regression or whatever. But at the end of the day, we actually, for the domains that people commonly work on, especially vision, we actually have a pretty good intuition what a CNN is doing, for instance, right? But when we switch over to this domain of invertible functions, I think a lot of the intuition that we think we have is wrong, and we've kind of lost and we have to relearn it. So that's actually the crux of it, is how to get that intuition. And the only way, I think, is by kind of some of the theoretical development, but also by just playing with them. And so I'll tell you one limitation that I'm aware of is, frankly, image quality. So if what you're really interested in is producing the highest photorealistic quality images from a generative model, GANs are the thing to beat, and normalizing flows are not it right now. That said, they're getting much better. So as an example, there was a paper at CVPR last year, which I believe for the first time reported FID scores and inception scores for a normalizing flow type model, which were competitive with some of the state-of-the-art GANs that are out there. But it's still, if what you tell me is you want the best, brightest photorealistic images you can possibly have, and you don't care about density evaluation or anything else like that, then normalizing flows are not there yet. I personally think we'll get there, but it's going to be a little time.
And you mentioned the density, if I can do a follow-up,
Sure.
the density estimation. So their normalizing flows have an advantage. So you're able to model more complex distributions. And how do you quantify that?
It's hard to say, because we can't easily compare negative log likelihood scores, for instance, against a GAN. And arguably we're training with different losses, so it's not even really clear if it is a fair comparison to look at negative log likelihood from a GAN. But yeah, normalizing flows, especially some of the most recent things, are basically becoming competitive with, for instance, autoregressive models, which, this is a tangent, but basically you can kind of view autoregressive models as a form of normalizing flow if you want to. They're a little bit unusual in that either the sampling or the density estimation direction is going to be a very slow calculation. But kind of more efficient normalizing flows are basically competitive with autoregressive models in terms of things like bits per dimension, or pretty close to it at this stage.
Awesome. Thanks for the insights.
Yep. I don't know who's next. Maybe
Mikhail?
Yeah.
All right. Hi, Marcus. Fantastic talk. Just fantastic work. Really cool. Yeah, I had two questions. So I guess the first one is, I guess just to some extent, there's domain knowledge going into setting up the choice of architecture for the normalizing flow, and so I was wondering if you could comment on that, and then secondly on just kind of as it's currently described, it seems to be free of hyperparameters aside from maybe the choice of architecture, and is that true, or am I missing something? Great.
So sorry, your first question, I apologize, can you just say that one more time?
Oh yeah, it was related to setting up the specific form of normalizing flow that one chooses to optimize.
Okay.
That seems to be a great opportunity to inject prior knowledge.
Yes.
But then at the same time, that's a bug too if you have to inject too much prior knowledge. So
yeah, so I think the way that I kind of approach this is I think, in deep learning, we have these kind of giant black box functions that have some amount of domain expertise that have been kind of, communally invested into them in terms of convolutions and striding and pooling and all these other things. Normalizing flows are kind of similar. We have this kind of fairly black box giant hammer that is things like affine coupling, coupling transformations and affine coupling models. And these and a lot of other variations that I haven't talked about today that are out there in the literature right now that are pretty much black box. You don't have to inject domain knowledge into them. What I find compelling is that because you're not learning a function, unlike a lot of other generative modeling approaches, especially like classical things, the function you're defining is not the density function itself. The function you're defining is the way a simple random variable is transformed to a complex one. And in my view, that gives a lot more opportunity for domain expertise to be inserted if you have it, right? If you don't have it and you have lots of data, then by all means, just throw more layers at it, throw more, more capacity at it with these black box flow transformations. But for instance, in the case of noise flow, we know we have, this really nice, it's almost a perfect setting for something like this, because we know that the noise process, the generative process, gets manipulated in certain very clear functional ways at certain stages of processing that we can very directly represent in the transformation. And in terms of your second question, you're asking hyperparameters. So I think it's pretty hyperparameter free in the sense that, you have the architecture that you choose to use. You have, your learning rate on, your stochastic optimization algorithm of choice, whether that's Atom or some other variation. There's not too many other hyperparameters that I can think of outside of those. So it's kind of, on par with your standard deep learning model, I would argue.
Cool, great, yeah. So for your noise flow, so would you get how much does the domain knowledge actually matter? So if you just threw in just a few more extra affine transformations to compensate for that you didn't know the existing structure, then would that still work just as well, or how? Yeah, I'm just curious.
It's an interesting question, and I actually don't know, because what's hard about that is that where the value of the domain knowledge comes is that we know that we want to condition on very specific types of information, and we know exactly how best to condition on that information. And so I feel like the ablation study you want to run is one where you construct a conditional normalizing flow that's kind of more generically conditioned on the clean image and generically conditioned on the camera and the ISO setting and things like that. And I feel like it'd be really hard not to construct a straw man as your baseline for something like that. So we haven't run that, and I'm not entirely sure what it would yield, to be honest.
Okay, great, thanks, great work.
Thank you.
I think Robin has a hand up.
Hi, thanks for the excellent talk. I wanted to ask you if normalizing flows are useful for generative models of tabular data, and also have they been used for RL models?
Yeah, so great questions. So for tabular data, absolutely. So I mostly talk about imaging applications because I'm much more of a computer vision person at heart, or at least I like to look at pretty pictures whenever I look at my results. But absolutely, people have run them on tabular data. In fact, some of the early papers ran on a lot of the test problems were for like the UCI, data set repository, and they generally show pretty good results on those sorts of things. It's the usual thing where when you have a tabular data set and you throw out all the structure of things like convolution and the spatial signal structure of an image, things get harder. But if you have enough data and the dimensionality is low enough, then they work pretty well. And I assume by tabular data, you basically just mean like a vector of numbers with no specific structure to them. Is that what you're asking?
Yeah, or like the type of data you might find in a database.
Yeah, okay. Yeah, so there's a slightly different question that you could have been imagining, which is if you have data that is discrete in some way, shape, or form. So for instance, language data being one of them, but having categorical variables and things like that. People have extended normalizing flows to categorical variables, and there's some interesting opportunities there for kind of joint learning of correlations between continuous and discrete variables. And so it does work okay in those spaces as well. I haven't played with that a lot myself, to be honest. And then you asked about RL. Yes, people have started looking at using normalizing flows to represent uncertainty in RL. I'm not an RL expert by any stretch of the imagination, but there have been a couple of papers that have come out over the last 2 years that have looked at applying normalizing flows in those contexts. So for instance, you can imagine if you had a policy over a continuous kind of continuous valued control signals, you could use a normalizing flow to represent the policy at any given point in time of your distribution if you want to have a much more kind of complex range of possible policies.
Thank you. Do you mind if I ask you a short follow-up?
Sure.
So, if you did have to model a state space that had continuous and discrete variables, you're saying that it might not be straightforward with vanilla normalizing flows, and it doesn't work very well in VAEs. What is there a go-to method for that problem?
I mean, so what I would say is I actually think normalizing flows would be somewhat uniquely well positioned to model data like that. But to my knowledge, I haven't seen a lot of people try it, and I would be excited to try it myself, to be honest. So if you have a problem like that and you want to try it, I'm happy to talk more about it afterwards. I think a lot of the other approaches that people have typically used for modeling kind of mixed continuous discrete data, they start to fall down when you have complex interactions between the discrete and continuous variables. And I think there's some opportunities with the way normalizing flows have been generalized to discrete data that would allow for those sorts of correlations and dependencies to happen much more naturally. But this is me mostly speculating at this point. So.
And then briefly, do you have to care about causality between the elements of XA and XB, like how you split the X? Does it matter?
Not really. There are some cute things you can do with the joint distribution if you care about causality between the way you split your dimensions. In particular, if you do a consistent split of your dimensions, what you can do is you can show that a normalizing flow with affine coupling layers is representing the marginal distribution of one half of your space, and then the conditional distribution of the other half of your space in order to represent the joint distribution. It's explicitly constructing both of those things in a very particular way. And so if you had an application where you really wanted to not only model the joint distribution, but also one of the marginals in the conditional distribution, you could do that actually nicely with a normalizing flow. And then you would have to care about causality between the dimensions.
Thank you.
Yeah.
Question?
Yeah, you showed the nice intuition that each coupling block is transforming your data step by step, and then it gets a normal distribution. But in practice, I cannot observe this. So is it really a problem, or should we solve this problem? Is it a problem? Should we go the way that Fjord goes? Or?
Sorry. I'm not sure. I'm not sure what you're asking. Like, are you saying we don't always end up with Gaussian distributions at the end?
Oh, no. The transformations are not smooth in every step. So you have your input data, then you transform it a little, then you transform more. So what I'm more observing is that all the deformation happens in one of the last blocks.
Yeah. So it's a great question, because there's an ambiguity. So normalizing, one of the things that makes normalizing flows nice is that, frankly, there's a really natural way to initialize the parameters of a flow, which is usually to initialize it something close to an identity transformation, because by virtue of being an invertible transformation, almost all of them can express an identity transform. But that also illustrates a potential pathology, which is that imagine if you have a distribution which we can capture with just a single block, but you fit it with 5 blocks or something like that, then the first 4 could do absolutely nothing, and the last one could do all the work. Is that's what you're referring to? Is that?
No, not really. So you showed that you have a chain of coupling blocks, right?
Yep.
And every coupling block does one transformation, then you get a new distribution, the next one does another transformation until you get a Gaussian. And you showed that this is really smooth. And
So I mean,
practice, it
it's
isn't.
not smooth for normalizing for coupling blocks actually. So and that I completely agree with you. So that was more of an illustration of kind of the intuition behind normalizing flows generally. What is true with coupling transforms is that the nature of the transformation is very limited for a single step of a coupling transform. Okay, because one is you're not changing half of the distribution, and you're only scaling and translating the other half in the case of an affine coupling transform. And so you can only express certain types of deformations of the distribution from one step to the other. And so you do need to chain multiple of them together in order to get a more expressive model. You can actually formalize this by effectively looking at the structure of the Jacobian of the transformation that you get when you have just a single one. And basically we know that you need to be able to have a dense lower triangular transform, and you don't get that with just a single step of a coupling transform. Now, there are, of course, as you alluded to, you mentioned Fjord, there are other measures, there are other normalizing flow models that actually explicitly represent a continuous transformation of the random variable in the form of a vector field or a differential equation. Those are really interesting models. I'm really keen on it, although on playing with those, and I've had students kind of playing with them off and on. Although I would also note that they actually exhibit the same pathologies as what you're alluding to a degree, because they can construct these really, really stiff differential equations that kind of ping pong around a space. And so there's the last year or so, there's been a bunch of papers, like 4 or 5 papers, I would say, over the last year, looking at ways to regularize things like Fjord to ensure that they have smoother deformations. So that cartoon is more aspirational and intuition than necessarily representative of exactly what you see with affine coupling transforms in practice.
Okay, thank you.
Yep.
Thanks. I think that's probably a good place to stop.
Okay.
So or we can thank Marcus either in virtual or physical clapping. Great. Thanks for coming, and hopefully once the whole COVID thing is over, we'll actually have you over physically, and
that would be great. Be lots of fun to actually come visit somewhere other than my office.
Yes. Sure.
All right.
Thanks a lot.
Thanks, everyone.
Thank you.
Bye.